Good evening, my dear JEE warriors. This is your Captain Shreyas on the Vedantu JEE English channel. Yes, your physics master teacher. Going live, training and mentoring kids for more than 15 years now. And now, here I am to take care of you. So quickly join in, invite your friends because the lecture has begun. And if you have not yet marked your attendance, quickly smash that like button and subscribe to the Vedantu JEE English channel so that you do not miss any of my classes which are conducted live and just for all of you in this Roar series, which is a proper JEE series. And now we have already reached magnetic effects of current and torque. And if you missed the previous class, let me remind you that in the previous class we had started off with, where did it go? Oh my god. Somewhere here, yes. Biot-Savart's law and Ampere's law, basically the sources of magnetic field. How current carrying wires produce magnetic field. How, different geometries and their formulas are obtained using Ampere's law. We have also seen how a coil carrying current is like a magnetic dipole, basically with two polarities, and how to calculate the dipole moment, etc., and how to explore that magnetic dipole around it by finding out its field and all such things. Right? We ended the class with gyromagnetic ratio in this first lecture of magnetic sources. Today we have reached basically the magnetic effects. Okay, and if you have not yet liked, quickly like the video, subscribe to the channel, and if you have not yet registered for MVSAT, quickly register for MVSAT. MVSAT is waiting for you. Not just national level competition scores you will get, because more than lakhs of students are going to write this test. You will also get a lot of rewards, goodies, and also scholarships on the courses and many such things. Also, a lot of free study material for just attempting the test. Online, it's on 10th to 20th October. Offline, it starts just 29th September. So make sure you are registered by entering the mobile number, sending OTP and submitting it. Okay. All other details, I have mentioned it before as well. Cool. And those of you who are wondering, sir, where can I get your PDFs and everything? Guys, it is there right over here. Where is it? The Jungle Book. See, this is the Jungle Book. Open the Jungle Book. You will get all my PDFs, notes, everything in one single place for all the three subjects. Okay. So that's where you can find it out. All right. So let's begin with the class. All are excited? Ready for it? Hi Joseph, hi Siva Prasad, hi Anand1, Joshua, Vijay. Good evening or good night. So Usha, good evening is always said when you are welcoming the person. Good night is said when you are leaving. So even you can say good night at 8 o'clock, no harm. But when you are leaving, you can even say good evening when you are meeting someone at 11 a.m. or 11 p.m. also. Okay, so that's how it goes. So, right. I will upload all those DPPs, Ashwin. Don't worry. Okay, don't worry. Hi Geeta, good evening. Hi Sairam, good evening. Nice to see all of you back. Right. So be regular. That's it. We are very close to the end. Don't you feel happy and proud about it? Where we started, how we started, and now we are reaching very close to the end. All right. So if you have a charge, it can apply some field on some other charge, and that field will apply a force. So this force is your electric force, and that electric force is given by the charge multiplied by the external field. This is your charge into that external field which is applied, gives me the electrical force. This is what we have studied in electrostatics chapter. Now we want to see, can magnetic field apply any force on other things? The answer to that is yes, definitely. Why not? We know that if you take two magnets like this versus like this, in each case there will be definitely some force. Here they will definitely repel. So that will be a force of repulsion. Whereas here, they will definitely attract. So the force will be towards each other. So there will be a force of attraction. So we can just say that magnetic poles can attract or repel basically each other depending on their polarities, just like charges. So therefore magnetic field affects poles. Magnetic field affects the north pole or the south pole, definitely. So that is one thing. But can magnetic field affect charges? Magnetic field can affect magnetic poles. Electric field can affect electrical charges. Gravitational field can affect gravitational mass, basically mass. But can a gravitational field affect electrical charge? Can an electric field apply a force on gravitational mass? It will be like an error 404. Hi Priya. Vijay, the class might end after 11 o'clock also. Who knows? Just go with the flow. Good evening, Dinesh. Yep. So we know that fields of similar kind can affect poles, charges, masses of similar kind. Electric field applies force on electric charges. Gravitational field applies force on masses. A magnetic field applies force on magnetic poles like north pole and south pole. Everybody fine till this point? Everybody fine till this point? Fair enough. If you wonder what might be the force of magnetic field in such cases, well, remember any magnet, let's say south pole as well as north pole, it is made up of magnetic polarities given by something like this, minus qm plus qm. These two things, they are basically called as the pole strength of a magnet. So this was our magnet. North pole is given a positive magnetic charge. This is a negative magnetic charge. So pole strength of a magnet, or basically magnetic charges. They are not having the unit of coulomb, rather they have the unit of ampere meter, and remember they are just pure scalar quantities. They are not even vectors. They are just scalar quantities. Also, if you draw a vector going from the south pole to the north pole, you will get the magnetic moment. M is the magnetic moment, like you had electric moment. So this is the magnetic dipole moment. This is the magnetic dipole moment, or just the magnetic moment. And the formula for magnetic moment will be any one of the charge. You take positive or negative, just the magnitude of that charge. Just take the magnitude of the charge multiplied by the distance separating both of them. So basically the length of it. That is basically your magnetic dipole moment's definition. Remember the unit of magnetic moment. The unit of magnetic moment will be ampere meter into meter. So ampere meter square. And it is a vector quantity. We have seen that in the previous lecture. We have seen that it is a vector quantity, if you remember it. Yes, this is 12th standard. Yes, Black Thunder. I hope this is clear. Everyone? Very good. Till this point. Okay. Now that is your magnetic dipole moment, which is formed because of charges. Electrical charges give you P, electric dipole moment. It was charged into the separation. Magnetic charges gives you magnetic moment. Notice, although the symbol is Q, but it is a magnetic pole or magnetic charge. It creates magnetic field. Okay, till this point, I hope it makes sense. Now, any magnetic polarity will experience magnetic force given by very similar looking formulas, just like in electrostatics. So say for example, there is a magnetic charge number 1 versus magnetic charge number 2, and they are separated by some distance r between them. Then the magnetic force which acts between them is just given by same or similar looking formula as Coulomb's law. Instead of 1 by 4 pi epsilon, it is mu naught by 4 pi, which is your constant, into charge 1, charge 2 divided by r square. Same looking formula like your Coulomb's law, guys. Similar looking formula. Mu naught is the permeability. Remember, your mu naught by 4 pi used to be 10 to the power minus 7 SI units. Right? That is what the value was. So charge 1 into charge 2 divided by r square. That is the magnetic force. Which also means that if somebody is looking at a bar magnet like this, and let's say over here there is a magnetic charge QM, maybe North Pole or South Pole, and some external field is there, some external magnetic field B is there. So this is from somewhere else it is coming. This is external source, some other magnetic field. This charge will definitely experience a force. This charge will definitely experience a magnetic force given by the charge again into the magnetic field. Charge into magnetic field. Just like in electrostatics, force is charge into field. We saw that. Force is charge into field. Same way, magnetic force is magnetic charge. This is not Coulomb's charge, positive, negative of proton, electron. This is north-south pole into magnetic field. It is in Tesla. Please mind it. This is Tesla. This is ampere meter. This is Newton. Is that okay? Everyone with me? So this is going to be in Newton. This is basically going to be in Newton. This is going to be in basically ampere meter, and magnetic field is going to be in Tesla unit wise. Keep that in mind. So all those formulas like Coulomb's law or force is charge into field are also applicable in magnetism. Don't think that there is no analogy or similar things. In fact, there is lot of similarities between magnetism and electrostatics. Hi Iron 1. All right, clear till this point? Very good. Awesomeness. Now, usually we do not discuss so many things about just magnetic charges. This was for your understanding that just like electric field applies electric force, magnetic fields apply magnetic force on magnetic polarities given by these formulas. But the strange thing that we need to talk about is, can magnetic field apply force on electric charges? They are of two different kinds on electric charges. It might seem very absurd. It might seem very non-probable because this is magnetic field. This is positive, negative electrons, protons. But the answer to this question is a yes. Long time back, people thought electric force and magnetic force are two different forces, like gravitational force, nuclear force, electromagnetic force. So it's a different primary force itself. Later on, Faraday and Maxwell saw to it that actually electric and magnetic forces are just two different manifestations or just two different avatars of the same thing. Just like you at school are a different person, but you at home behave very differently. But at the end of the day, you are the same one. It's just that you are showing different behaviors. So same way, people realized it later on, just couple of 100 years back, not very long before, that electric and magnetic forces are, just two different ways of looking at it. And hence, it didn't seem very absurd then that magnetic field can also apply forces on electrical charges. So it can apply, and only in some cases. In some cases. So we will see what those cases are. Okay? So definitely if you have a magnetic field, but this time this is your electrical charge, definitely there can be a force acting on it. Definitely there can be a force acting on it. Now, the strange thing for that is, this particular force acts not in the direction of the field. Yes, not in the direction of the field. Say for example, you have a charge. Say for example, you have a charge, and let us say that the magnetic field is like this. This is the magnetic field. If this charge right now is at rest, they found that there was no force only acting on it. The force on it was 0. So no force on charges at rest. On charges at rest, basically static charges. On static charges. That is what they saw. But the same charge, let's say it is moving like this with some velocity. Let's say it is moving like this with some velocity. And let's say the magnetic field at that particular place is in this direction. Then, or let's say, we'll do one thing. Let's say it is moving like this, and the magnetic field is in this peculiar direction. Then they found that the force acts perpendicular to the velocity also and perpendicular to the magnetic field also. Yes, the force acts perpendicular to both velocity and magnetic field, but there can be two perpendiculars like this or like this. So they found that the direction is in the direction of taking your right hand fingers, pointing it towards V, then towards B. So wherever V cross B points, the cross product of V cross B, that is the direction of the force. So they just saw that the force is perpendicular to both. The force is perpendicular to both magnetic field as well as the velocity. So hence they said or found out that force is nothing but Q into velocity cross producted with the magnetic field. Cross producted with the magnetic field. This is what the formula was found to be via experiments. This is experimental. And this force, in the next page, I will write it down. This force was found to be perpendicular, to both the velocity as well as the magnetic field. Also remember, this equation is sensitive of the sign of the charge. If it's a proton, I'm multiplying it with a positive charge, so the force is as shown. But if it was an electron, which is a negative charge, so multiplying this equation with a negative sign will just flip the direction of the force. So it will be V cross B, but with a negative sign, which is same as B cross V. So you need to be careful that outside this charge is not the magnitude, but it comes along with the sign. I hope this is clear. Yeah. Football edits, just send me your, a screenshot on my Telegram, right? I will look into it. Okay. Just share it to me. Okay. I'll just look into it. But I feel that slowly it is coming to all the students. Just recently I spoke, some students have started getting it. So maybe there was some delay for some reasons. Just send me your screenshot on my Telegram, captain_Shreyas. Cool? Okay. Yes, looks like motional EMF formula, definitely. Now the interesting thing is, because the force is perpendicular to the velocity, that means there is a very interesting thing which is happening. The work by the magnetic force, force on a moving charge is basically zero. Force is perpendicular to the instantaneous displacement at every single instant, which means it can't do work. And what does work energy theorem say? If you can't do work, you can't change its kinetic energy, which means you can't change the speed. Therefore, this magnetic force can't change the speed, very, very important, but can only change, what can it change if it can't change the speed? Only change the direction, can only change the direction. So very, very important. So this particular magnetic force can only change the direction, but it can never change the speed. It can't change the speed, but can only change the direction. Very important for solving problems. Hi, where finds. Okay, we'll come to all these questions in a separate session. That will be better. All right. Cool. Okay. I hope this formula is absolutely stuck in your head now. Charge into V cross B. Charge into V cross B. Great. So that is what is there in the starting part of this particular lecture. Let's take some examples to really understand this so that it's there in your head. I will give you certain scenarios and you are going to tell me the direction of the force in every case. This is a positive charge which is going like this. This is negative charge going like this. Then a positive charge, let's say, going like this. Then positive charge, let's say, going in this direction. Then let's say a negative charge going like this. And let me show now the direction of the magnetic fields in every case. First scenario, it is like this. Next scenario, let's say it is like this. Next scenario, let's say it is like this. Next scenario, let's say the magnetic field is inside. Here, the magnetic field is coming towards you. Okay, so in each scenario, figure out the direction of the force. That's all I'm asking you. Okay, just figure out the direction of the magnetic force. First scenario, if you notice, velocity and magnetic field, V cross B, right? Velocity and your magnetic field. So magnitude wise, it is VB sine theta. Yes. Awesome. Thank you, Football Edits, for sending the screenshot. Okay, JEE will come to how to revise all the syllabus after a bit. Let me just cover most of the syllabus. Yeah, kinetic energy will be constant, Ibrahim, if only magnetic forces are there, because it can't change the speed. That means speed is constant, no work is done. In the first case, can you see that theta is 0? So sine of 0 degrees is a big fat 0. They are parallel. So hence the force will not be even there in this case. In fact, there is one more diagram where the force is not there, and I think it is this one, because if you notice, it is 180 degrees and sine of 180 degrees is also 0. So in this case also the force is 0. So even on charges which are moving, the force can be 0. Just because velocity is there does not mean force will act. If magnetic field makes 0 or 180, then gone, no force will act. Making sense? In this case, if you see, velocity is up, magnetic field is towards right, V cross B will make your thumb go inside, but it's a negative charge. So multiplying it with a negative number, you will get the vector coming towards you. So the force is coming towards you out of the plane. Velocity cross B goes inside, the negative charge will flip it. Here, magnetic field is going inside, velocity is towards the right, V cross B, velocity is towards the right, cross B will make the thumb go up, hence the force acting on this will be upward. Here, the charge is going down, magnetic field is towards you. So you'll have to do it a little bit. V cross B will make your thumb go V. So take your right hand, open it like this. You have to do like this. It's going down. It's going to put some strain on your muscles. V cross, it's actually going like this. V cross B. You have to try it out. You have to try it out. Velocity is down. Magnetic field is towards you. Will make the thumb go towards the left, but it's a negative charge. So hence you should go towards the right. So that's the direction of the force. Is that clear, everyone? Just check it out. Everyone? Yeah. Great, great. Cool. Till this point, understood? Let's go ahead. Let's go ahead. A proton of 10 to the power minus 27 kg, 1.6 10 to the power minus 19 coulomb, goes in a magnetic field of 2 millitesla at 100 meters per second, making 30 degrees with it. Making 30 degrees with it. Question is, find number 1, the force, number 2, the acceleration at that moment. Find the force as well as the acceleration at that moment. Let's try to solve this. I know the field, I know the speed, I know the angle, I know the charge. Q, V, B, sine theta, I need all these things. So to find the force is a straightforward task. Q, V, B into sine theta, because cross product means sine of angle between those two things. Charge is 1.6 10 to the power minus 19. Velocity is 100, so 10 to the power 2. Magnetic field is 2 into 10 to the power minus 3. Sine theta means sine of 30 degrees. So let's see what does it come out to be. Now 10 to the power 2, 10 to the power minus 3 will make it 10 to the power minus 1. So this power will become 10 to the power minus 20. 1.6 is as it is. That 2 is remaining. Sine 30 is basically half. 2 cancels. So I'm left with just 1.6 into 10 to the power minus 20 Newton. This is very, very small force as expected. If you thought the answer will come in few newtons, you should be surprised. It is not. Now you might be wondering, sir, the force is so small, sir. Why are we even studying this chapter? Ignore this chapter. We ignore so many things. This is 10 to the power negative 20. But the very interesting thing happens when you try to find the acceleration, which is force divided by mass. So 1.6 10 to the power minus 20 divided by the mass, which is 10 to the power minus 27 kg. What does that acceleration come out to be? These two cancel, it will become 10 to the power 7. So 1.6 into 10 to the power 7 meters per second square. Even though the force is small, it is acting on a very teeny mini mass at atomic level. So the acceleration is very, very large. So we can't ignore such things. Yes, we can't ignore such things. Yes, we have used F is equal to ma. Okay, gravitation we'll do later on, where fun finds you after rotation, because till rotation I don't want to do that, because angular momentum, all those concepts are there. So after rotation only we'll do it. Is this clear? Why we study this particular chapter? Understood? Right? Let's go now to the next part. Now that you understood, okay, this force is important. You might be wondering, sir, what will happen if both electric and magnetic fields are there? What will that charge do, sir? So let me tell you, this charge is there. Let's say it is already moving with some velocity, and maybe there is a magnetic field which is acting like this, because of which there could be a magnetic force. There could be a magnetic force which acts in this particular direction. This is the magnetic force, which is obviously perpendicular to this also and this also. Okay. At the same time, maybe there is an electric field somewhere. Maybe there is an electric field, and maybe the electric field is in this direction. Maybe the electric field is in this direction. Because of that electric field, there will be an electric force, and that electric force is always in the direction of the electric field. So this is the electric force. So if you ask me, the electric force and the magnetic force, what is the values of it? Well, electric force will be charge multiplied by the electric field, whereas magnetic force will be charge into velocity cross producted with the magnetic field. So what will the charge end up doing? Will it listen to this or this? Rather, it will listen to both, and you will see that if you use the law of parallelogram of vectors or triangle law or whatever you want it, okay, and then you'd find the resultant, this whole thing, this is the resultant, guys. That is the net force. So it will experience net force due to both the fields, that F will be simply put this thing, which is electric field force plus the magnetic field force. So you can see both of them have charge. So I can take charge common, and it will be addition of two things over here. One is obviously your electric field, and plus velocity crossed with magnetic field. So that is the net force acting on it. So this force, which is the net force, is often referred to as the Lorentz force. The net force is often referred to as the Lorentz force on charges. Is this clear? It's just that the vector sum of both of these two things are taken as the net force, and that is what you are calling as the Lorentz force. Nothing great, very straightforward. Shyam, the Jungle Book is basically an entire PDF of all the lectures, so you don't have to go through the YouTube playlist. Don't spam, first of all. Even if you would not have spammed, I would have answered it, Shyam. So if you are new to the channel, please remember this. It has all the lectures, their notes, their DPPs, and more things will get added, like for BITSAT, VIT, for MHT CET, alright, for KCT, ComEd-K, we are going to update that entire book, okay, right? So that is a Jungle Book. So you don't have to always look, okay, sir, I forgot where this lecture is. The Jungle Book, if you save that link, always you can use that link for studying any particular chapter. Cool? All right. Now let's take an example of this. For example, the electric field is 2I cap. The magnetic field is 3J cap. At t is equal to 0, a positive charge is at rest. Can you show the path for initial duration? For that initial duration, can you just show how that motion would look like for that particular particle? Let's try to analyze the situation slowly. This is your x-axis, this is your y-axis, this is your z-axis. Okay, think carefully now. How will the particle move initially. Electric field is 2 I cap, that means electric field will apply a force here, and that charge, remember it's a positive charge, so the force due to electric field will also be in this direction. It will be charge into electric field. Magnetic field is in the J cap direction, so it will be like this. But remember one thing, when there is no velocity, it is at rest, initially velocity is 0, so V cross B will be 0, therefore magnetic force is 0. Because magnetic force is 0 and electric force is not, but electric force is along the x direction, therefore initial motion will be along x axis. Initial motion will be along x axis. So 100% the particle is starting to go towards this side. But the moment it starts even moving slightly after t is equal to 0, that is after delta t, okay, that is t more than 0, what happens? Velocity is there. In fact, velocity is along x-axis, and it is not 0. So V cross B, how will V cross B be pointed? Velocity is here, magnetic field is in this direction, guys. Think about it. This is the direction of the magnetic field. V cross B will be towards you. V cross B will be along the z axis. So hence the magnetic force will be along the positive z axis along with which other force? Electric force along the positive x axis. So what will happen? This particle will go like this. It will definitely turn this side because of this z axis force. So the path taken will be slightly curved. So it will be a curved path because of the magnetic force and electric force. That will be the initial path taken by the particle. So it will move essentially, if you combine all these results, it is having a motion in xz plane, and that is a curved motion. In the xz plane. So you can have options like this: a curved motion in xy plane, a straight line motion in xz plane, curved motion in zx plane, a curved motion in zy plane, something like that. So then you will choose the correct option as per this analysis. Is this clear? Yes? All right. What is the next lesson based on? It is basically we are going to do, say circular motion is done, we'll do center of mass, collisions, rotation, and then we'll come to EMI. That is the flow. Okay, center of mass, collisions, rotation, we'll do it together, like one after the other, and then we'll come back to electromagnetic induction. Is that okay? Yeah, that is the plan. It's there already there in the upcoming schedule. Every week you will start seeing the upcoming classes. Great. Let's do one more question coming up on your screen. If a charge of minus 2 microcoulomb is moving at 10 meters per second in fields of 20 volts per meter in y-axis and 10 Tesla along minus x axis, find the net force acting on it. Find the net force acting on that particular particle. Let's try to do this question. It's a direct application of Lorentz force, nothing more, nothing less. So I think charge is given, speed is given, directions are given. Acha, direction of the speed is not given, so I need to mention that is moving 10 meters per second along let's say z axis. That needs to be mentioned, along z axis. Okay, now it is fine. So let's try to do this problem. First, let's try to find the electric force. Electric force is charge into the electric field. Charge is 2 microcoulomb with negative sign. So 2 micro is 2 into 10 to the power minus 6. And electric field is nothing but 20. So it will be nothing but minus 40 into 10 to the power minus 6 Newton. So that is your electric force. Minus 40 into 10 to the power minus 6 newtons. Let's try to find the magnetic force now. The magnetic force will be the charge, which is minus 2 into 10 to the power minus 6. Velocity is 10 along the z axis. That means it is 10 k cap. Cross producted with magnetic field of 10 Tesla is along the negative x axis. So minus 10 I cap. This is Tesla along the negative x axis. So what will this become? 10 into 10 is 100. So this will become minus 200 into 10 to the power minus 6. Minus minus becomes plus. This minus and this minus becomes plus. What is k cap cross I cap? If you have forgotten, remember this simple rule. Write I, j, k in the clockwise manner. If you go clockwise, it is positive. Anti-clockwise is negative. So k cross I. So k cross I should be clockwise. So it is positive. So it will give me j cap. So hence, this answer will be positive j cap. That is what magnetic force is coming out to be. So now I want to find the total force. So I want to find out the total force. So hence, it will be, oh by the way, electric field was in which direction? It was in y-axis. So this was basically j cap. So this was j cap. So hence, the force will be minus 40 into 10 to the power minus 6 j cap plus 200 into 10 to the power minus 6 j cap newtons. 200 minus 40. What is 200 minus 40? 160 into 10 to the power minus 6 j cap newtons. That is the final answer. 160. How many of you got it? First time joining the live, were you watching recorded before this, or first time attending on this channel itself? If you are attending for the first time, subscribe, very important, and keep following the Roar series, which are live classes for your JEE preparation. After the syllabus, we are going to start with problem solving, mock tests, etc. Cool, is that right? Everyone got this point? Yeah, now I hope, Ibrahim, you are able to get the directions. Harshit, right now I'm in Bangalore, but have done my education in Maharashtra. Yeah, born in Tamil Nadu, a lot of things. Cool. Now that you have understood how this particular Lorentz force works and how to solve the basic questions on it, let's start taking different special cases of the charges in magnetic field. The first peculiar case is when the charge is either parallel or anti-parallel to the magnetic field. When such thing happens, you will notice that when you take the cross product of the velocity with the magnetic field, the answer for that will be a big fat 0. Reason is sine 0 is also 0, sine 180 is also a 0. Hence, the force of magnetic will also be 0, which means the motion will be a straight line motion with constant velocity, with uniform velocity. There is no change at all. It keeps on moving in a straight line. There is no reason for it to change the direction. So the path taken will be a straight line. Is this very, very clear? If it was at rest, it will stay at rest. But since it is already in motion, it will continue its journey. There is no need to react because no magnetic force is there. I'm so glad, Sushant, you understood this question. Great. First simple case. Now we'll go to the second case. Now the second case has many questions in your JEE examination. Most of the papers, if you see, around 60% or 50% of the times, just this special case is asked in your JEE examination. Okay, so that's why this becomes the most important case. So basically, it is just called as transverse magnetic field. Transverse motion in magnetic field. Now, when I use the word transverse, it means perpendicular. So the velocity is perpendicular to the magnetic field. So just imagine our magnetic field is something inside the plane or outside the plane of the board, and it is there everywhere. It is there everywhere. So this is the magnetic field inside. So to draw perpendicular, I can go like this, I can go like this, I can go like this. Anywhere in the plane of the board, if I go, it will be perpendicular because the field is inside, and anything perpendicular will be in the plane of that particular board, in the plane of that particular board. So let's say I have a charge which goes probably like this. I have a charge which goes probably like this with some velocity. I have told you before, when I discussed how this force acts, it is always perpendicular to the velocity. It never does work and only change the direction, but never change the speed or its kinetic energy. That is what I had discussed initially. Hence, think of all such conditions where the speed can't change, direction can change, and the force, in fact, is going to be perpendicular. Now, all these conditions have to be satisfied, which means there is only one thing which it can do. There is only one path which it can take. Sagar, this is mains plus advanced because I'm covering the entire mains topics, advanced topics, all difficult questions, easy questions. I'm laying the complete basic foundation. Once we come to problem solving, we will be solving even more questions. So first is concept plus applications in the questions format, and then we are going to go to pure mock tests and revision sessions. Is that right, Sagar? Okay. So what happens? This can only happen in the case of uniform circular motion. Yes, you heard it right, uniform circular motion. So the path taken by it will be a uniform circular motion case. So something like this, it will go in a uniform circular motion. So even when the particle is over here or even over here, you will notice that the force will always be directed towards the center. It will act like the centripetal force. Hence, it is a uniform circular motion. So let's assume that the radius of such a circular path is, let's say, r. This is the center. Okay, uniform circular motion. So I can just say that the magnetic force provides the centripetal acceleration. Centripetal acceleration. So F is equal to mass into acceleration. Magnetic force is charge into velocity into B. Angle is 90 degree. So sine 90 is m into acceleration is v square divided by r. Correct? So your velocity will get cancelled. Sine 90 is 1. So therefore, I just get Q B sine 90 being 1. Mass is there, V is there, divided by R. Rearrange it further. You get R is equal to mv divided by qb, or you can also say this is momentum divided by qb. Momentum is nothing but root of 2 times mass times the kinetic energy. So that also you can do. So depending on what is given to you, Is it kinetic energy, is it momentum, or is it speed? Accordingly, you can change the forms, but usually, if you remember this, you can easily convert it into anything else also. So this is the main formula for the radius of the charged particle in that perpendicular magnetic field. The particle performs uniform circular motion. Yeah. Okay. Sushant, which books am I telling you these topics? This is NCERT plus your HC Verma or basically your JEE mains and advanced syllabus combined. Remember, JEE mains has a prescribed syllabus, advanced has a syllabus. If you combine them both, this is what it is. Now, whether you talk about MHTCT, KCT, COMEDK, EMSAT or VIT EEE, they all derive the syllabus from any of these things only. So if you study for them, automatically you are preparing for all the engineering entrance examinations. The next thing is to figure out what is the time period of revolution. So I can say that the time period of the circular motion is nothing but, time is distance by speed. So it will be circumference. It will be nothing but the circumference divided by the speed of revolution. The circumference will be 2 pi r. Speed is basically v. So it will be 2 pi divided by v. R is nothing but mv by qb. mv by qb. Velocity will cancel and I'll be left with 2 pi m divided by qb. That's your time period. And again, better remember this. If they ask you frequency, just flip it. Interesting thing is, it's independent of what? It's independent of the velocity. Very, very critical. It's independent of the velocity. No matter how fast you throw it, it will always take the same time. You take the same charge, throw it, you will see, if you take the same charge, you throw it, it might go with smaller radius or bigger radius, but it will come back at the same point in the same time, assuming the same charge of same mass is thrown in the same field. That's very interesting. It's independent of the velocity. Is it clear? This is class 12th topic. Magnetism. Yeah. Class 12 topic. All these things I have already mentioned over here. Okay. Now let's take some examples for this. Let's take some examples for this. Say, an electron is moving, or electron is accelerated by a potential difference of, let's say, 2 kilovolt in a transverse field of 0.1 Tesla. Find the radius and the frequency of the uniform circular motion. Find the radius as well as the frequency of the uniform circular motion. One thing is clear, why it is going in a uniform circular motion is because it's a transverse field. So definitely there will be some radius involved and there is some time period involved of that particle. Okay. Now we can find the radius using the standard formula. So R is nothing but mv by qb, but the problem is I don't know the speed only, but it is given the electron is accelerated by a potential difference, which means it has got kinetic energy from where? From the loss of the electrical potential energy. So electrical energy got converted into kinetic energy, which means charge into potential difference is equal to half mv square, is equal to half mv square. Okay, I hope this is clear. Or I can just keep it as kinetic energy for now. I can just keep it as kinetic energy for now. So the charge is 1.6 10 to the power minus 19 It is accelerated by 2 kilovolts. So 2 into 10 to the power 3. That is your kinetic energy. Therefore, kinetic energy will be 1.6 into 2 is basically 3.2, and this will become into 10 to the power minus 19 plus 3, or 19 minus 3 is nothing but 16. Okay, so minus 16. So that many joules of kinetic energy it has. Keep this aside. Now we know that the radius, I just told you before here only, radius is mv by qb or momentum by qb. Momentum is root 2 times of mass of kinetic energy and then divided by qb. I feel using this will be a long way. This is easier. I just directly substitute kinetic energy. So that's how I can do this problem. So it will be root of 2 times m times kinetic energy divided by charge into field. So what is it going to be? 2 times of mass. Electron has a mass of basically 10 to the power minus 31 approximately. Kinetic energy is basically 3.2 into 10 to the power minus 16. Whole thing divided by charge, which is 1.6 10 to the power minus 19 into magnetic field, which is 0.1. So what will it come out to be? Let's figure out. Okay, 2 into 3.2, that's basically 6.4. Minus 31, I'll do one thing. I will make it, okay, let's just write it like this. 3.2 into 10 to the power minus 31 minus 16. That's going to be minus 47, the whole thing divided by. This is a decimal, so minus 20. So it will become again 16 into 10 to the power minus 21. Let me shift the decimal, it will become minus 46. So, sorry guys, this was 6.4, not 3.2. 2 into 3.2 is 6.4. And minus 31 and minus 16 will make it minus 47. So let me write this down as 64 into 10 to the power minus 48. I just shifted the decimal, so an extra negative power. And this is obviously 16 into 10 to the power minus 21, which will make it as what? 64's root 8 minus 48's root will make it 10 to the power minus 24 divided by 16 into 10 to the power minus 21. 8 by 16 is 0.5 into 10 to the power. This is making it 10 to the power minus 3 meters, basically 0.5 millimeters. So 0.5 millimeters should be the answer. Is that right, everyone? Till this point clear? Once I get the radius, finding the frequency, not so difficult. Frequency is 1 by time period. Time period was 2 pi m divided by qb. Doesn't matter what the speed was, so don't worry about that acceleration part. Charge is 1.6, 10 to the power minus 19. Magnetic field 0.1 divided by 2 pi, and mass, which is 10 to the power minus 31. Okay, so therefore frequency will be, you can write it as 16 by 2, which is 8, and of course that pi will stay below only. I will write 1.6 as 16, that means this will become 10 to the power minus 20 and one more power, so 10 to the power minus 21 divided by, this is 10 to the power minus 31, so frequency will become 8 by pi. This will make it 10 to the power 10, but this answer will be in hertz. So 8 by pi, 10 raised to 10 hertz. That is the answer. So that's very, very large number of revolutions per second, and that's an extremely small radius, 0.5 millimeters. That's small. Zzz, it will keep rotating, and so many times, 10 to the power 10 times. That's so many revolutions in 1 second. Is that clear how we solve these questions? These kind of questions can come in your JEE examination. This was also important where I accelerated the charge. So electrical energy got converted into kinetic. Electrical energy is charge into voltage difference. Let's do some more questions. Imagine it's given that an alpha and a proton alpha particle and a proton are thrown in a transverse magnetic field, with number one, with same number one speed first time, second time with same kinetic energy. Question is, find the ratio of radius and the time period. Find the ratio of the radius as well as the time period. Let's solve this case first, speed, then let's solve the kinetic energy case. Okay? So first let's solve for speed, then let's solve for kinetic energy. Now, if I want to find the ratio of the radius, I need to know the radius formula, which is nothing but mv divided by qb. It's thrown with the same speed, v is same field, that means b is same, mass and charge will be different. So r is basically directly proportional to mass by the charge. So radius of alpha by radius of the proton will be mass of alpha by mass of proton. Here you will have charge of proton and you will have charge of alpha particle. The mass of alpha particle as compared to the proton is 4 times the mass. A proton is just one proton, alpha will be 2 protons, 2 neutrons. Neutrons and protons have roughly the same mass. That's why 4 times of this multiplied by. Proton is 1 positive charge. This is 2 positive charges because of the 2 protons. So the ratio will be 1:2. Hence the net ratio will become 2:1. So radius of alpha and radius of proton are in the ratio of 2:1. Correct? Now let's do for the next part, which is time period. Time period being 2 pi mass divided by charge into B is directly proportional to mass and inversely proportional to the charge, just like this one. So the time period of alpha by time period of proton will be mass of alpha, mass of proton, charge of proton, charge of alpha, exactly the same thing. So time period of alpha and time period of proton will be just again 2:1 only. Will be just 2:1, no difference at all. Thank you, Krutik Pranav. Where are you from? Hi, Ari Varsu. Welcome to the Vedantu JEE English channel. Welcome to the road series. The second part, I'll tell you, the time period is still going to be having the same ratio, because no matter what the speed is, time period is the same. So time period is still proportional to mass, inversely proportional to the charge. So therefore, the ratio of the time periods of alpha and proton will still be 2:1. Just like before, there should be no change. The problem happens only for the radius part. Remember, radius was mv by qb, which is also root of 2mk divided by qb. That means it is directly proportional to root of mass upon the charge. 2 is constant, k is constant, b is constant. So radius of alpha by radius of proton will be root of mass of alpha by mass of proton. Here charge of proton, charge of alpha. That is what it is. Mass of alpha is 4 times mass of proton. Charge of proton is 1e, alpha is 2 times. Root 4 is basically 2. So into 1/2, which means the ratio is 1:1. So they are equal. They're just going to be equal. That's it. Is that clear, everyone? Understood how to solve this question? Shall we move ahead to the next one? Yep. Yes, Muruga, just like Bala said, this is for class 12th. Class 11th, we just completed circular motion. Next time we are going to do the center of mass tomorrow only at 5 o'clock. Let's go to the next question coming up on your screen. All these are very popular questions. That's why I'm doing some examples on this. A charge Q enters a narrow field B of width L perpendicular to the motion, with a speed u. Find the maximum time it can spend inside. It can spend inside the field, number one. If the width is halved, for the field, find the deflection as it exits the field. So there are two parts of the question. We'll do it one by one. We should go one by one. This part we'll do it later on. First, let's do this, then we will do this. Okay, as compared to the previous one. Okay, let's go part by part. Okay, so basically we have a charge which enters a field of certain width. It's perpendicular to the motion. How much is the maximum time it can spend inside? That's the question. So let's think of a region of magnetic field. Maybe that region of magnetic field is right over here. Now, let's just say this is that region where that magnetic field exists, and this is basically your length L. Now, imagine a charged particle entering inside like this. It will get deflected, so it will start going like this. It will come out and come out from here. If you give it some more speed, then it will go here and it will come out like this. If you give it even more speed, then it will come out like this. I hope you can visualize it. If you give it even more speed, then it will just exit out from here and that's it. It will never return back. So when it has to spend maximum time, what should exactly happen? When it has to spend maximum amount of time inside this, what exactly should happen? Okay, it's not possible for me to draw using this regular thing. So just visualize this. It should basically go like this and come out from here, or it should basically just come out from here, enter from here. Anything below this is fine, like it can go like this and come out, no issues. But anything more than this, it will just exit out. That's what will happen. This is going to be very small time. This is going to be very small time. This is going to be for a long time. This is going to be for a long time. Here also this is not long time because the red one, it stays only till here. It is not spending more time. It is just going to exit out from there. So to find out the maximum time, I can see that it is completing half a circle. So it's doing half of the complete uniform circular motion. So the maximum time, shouldn't it be the total time period of the uniform circular motion divided by 2? And I already know what that time is. It is 2 pi m divided by qb. So 2 cancels and I'll just get it as pi m divided by qb. So that's the maximum time it can spend. That's the maximum time it can spend. Agreed with this? Clear? Yep. Awesome. Gamer Zone, I just made a video for this. In case you have not seen it, please check it out. I have made a video. Where is it? For JEE Advanced Preparation, what is the book that you can use? And I have given all the details regarding the book. Just check out this video. This is mainly for advanced. Okay. And if you just want for mains and advanced a combination, but more of mains, then I would suggest you to check this particular out, the complete books for your JEE preparation. Okay, I have given that in this particular video. Okay, fair enough, Gamer Zone. Okay, now when this happens, you know, our interesting thing should be noted. The width of this also becomes the radius. The width of this also becomes the radius. So if I write it down properly, the radius is equal to the width. Radius is mv by qb. So that is what it will be. So rather u will be equal to qbl divided by m. This is what I get. The speed by which it enters here will be qbl divided by m. This is needed for the next part. Because the next part says, if the width is halved, then what is the deflection? Interesting. So just imagine now the width is halved. Width is not as much as before. So now the width is basically L by 2. But when it enters, it does not know that the width is L by 2. It continues thinking, I can complete the semicircle, but it can't. Rather, it just does a part of the circle, and after this, it exits out with that same speed. So it will get definitely deflected by some amount. It definitely gets deflected by some amount. We have to exactly find how much that particular deflection is. I know one thing though, the radius wouldn't have changed. The radius wouldn't have changed during this. So whatever the radius was there before, it's still the same. In fact, remember the radius was L before. The radius was L before. So therefore, this radius being L helps me solve the problem. How? Observe carefully. Let me just drop a perpendicular. Maybe that will help me. Just completing this horizontal line now. Okay. I can see a beautiful right angle triangle getting formed where the hypotenuse is L, the base is L by 2. Can you see that beautiful triangle? The base is basically L by 2. The hypotenuse is L. What is this angle going to be? This angle is just going to be 30 degrees. So if this angle is going to be 30 degrees, this angle is also going to be 30 degrees. That means this angle over here is going to be 60 degrees because this total should be 90. If that is 60, that means this theta should be 30 degrees. Hence, I just get that the deflection is how much? 30 degrees. Done and dusted. So a complex problem was actually simple if you do it properly by geometry. Hi aesthetic me, welcome to the Vedantu JEE English. Is it absolutely clear how we did this kind of question? So these kind of questions are very, very common, guys. In your JEE examination, you should know how to do all of them. Okay, sometimes kinetic energy will be asked or given, sometimes it will be accelerated, okay, sometimes the radius will be asked, time period will be asked, it will be passed through a field, deflection could be asked. Everything is related to uniform circular motion. Okay, cool. Now, what happens if the motion is not perpendicular, motion is at an angle to the magnetic field. A very interesting thing will happen. A very interesting thing will happen. Let's see if you are able to visualize this. This is the x-axis, this is the y-axis, and this is the z-axis. Okay, so just imagine I have a charged particle and I'm giving it some velocity, maybe like this. I'm giving it some velocity like this, and the magnetic field is in this direction. The magnetic field is in this direction. So now what you will see is that I can take two components of the velocity for my simplicity's sake and then solve the problem. So one component of the velocity, I will take it in this direction, okay, which will be velocity's cos component, and the other component will be like this, which will be sine component, v sine theta, v cos theta. This was basically your theta. So one component is v cos, the other component is v sine theta. Out of these two components, tell me where will magnetic field not apply a force? Where will magnetic component not apply a force on? Hi Yashas. Try to recollect the formula, velocity cross B. If velocity and magnetic field are in the same direction, angle will be 0, sine 0 is a 0. So this component, won't there be any force? Yes, there will be no force on this. No force on this because velocity is parallel to the magnetic field and sine of 0 is 0. Cross product will be 0. But this guy, definitely there is a force and velocity is up, magnetic field is right, V cross B will go inside. That means the force will be in this direction. This force is on that particular charge with that velocity component V sine theta into your magnetic field. So it will be like that. I hope you are able to visualize it inside the plane of the board. So what will happen? Because of that particular force, think about it, because of that particular force. First of all, let's forget this separately and let's forget this over here separately. Take each components. Because there is no force on V cos theta, so therefore this V cos theta component will be basically a constant. Hence, this component will ensure that the particle is going forward in a straight line with uniform velocity. But this component is perpendicular to the magnetic field. Do not forget that magnetic field was over here. This force will ensure that the motion of the particle is in circular path in the YZ plane. Try to visualize this now. It's in the YZ plane. Are you able to visualize this? Is the real challenge now. It's performing uniform circular motion because of that force. The center of the circle is here. This is UCM in the YZ plane. Are you able to visualize this? Everyone? Good evening, everyone. What would be the radius of it? What would be the radius of it? Well, radius formula I have already given. Mass into velocity, in this case the velocity is V sine theta, divided by charge into B. What is the time period? 2 pi m, speed doesn't matter, divided by QB. So it performs UCM because of one component, and because of the other component it goes in a straight line. But both the components are actually present together. So it is going in a straight line along X, and it is also doing circular motion in the YZ plane. So just imagine something going round and round, and at the same time it is going along its axis forward. So how would such a motion look like? Round and round, but the plane keeps changing. The plane in which it revolves keeps changing. So the plane keeps shifting along the axis. That motion is called as a helical motion, basically like a spring. Basically like a spring. It looks something like this. This is spring-like motion, so it will look like a helix or like a spring. Okay, very, very important, guys. So the motion of such a thing is basically a helix. Helical motion. After one revolution, if you notice, if it started from here, after one revolution, it came here. Again, after one revolution, it came here. The distance between those 2 points after one revolution is also called as the pitch. Pitch means win one revolution, how much do you go ahead? That pitch can be calculated easily, not that difficult. Remember, our horizontal speed never changed. So, horizontally I am moving with a constant speed. In one revolution, basically I take this much time, 2 pi m by qb. So, how much do I move ahead? So, the pitch is basically your horizontal or axial speed multiplied by the time period of revolution. Multiplied by the time period of revolution. Therefore, you will see that the pitch of the helix will be v cos theta multiplied by time is nothing but 2 pi m divided by qb. That is what it will be. The radius of the helix is just like before. So the radius of the helix will be m into v, but sine theta, m into v sine theta divided by charge into magnetic field. That's it. So that's the formula again which you should know. Mainly remember this, guy. Pitch is axial speed into time period. If you know this, you can easily write this down because you know this and you know this. Radius of the helix is just like before, so there is no change at all. Except for v, you have v sine theta. Is it clear? Spring-like motion. Yes. Hi FF Trent. Good evening. Let's do a numerical question on this. Mass is 2 grams. Charge is 4 microcoulomb. Velocity is 100 meters per second. Magnetic field is 0.01 Tesla. The angle between velocity and magnetic field is, let's say, 37 degrees. Question is, find the pitch and the radius. Find the pitch and the radius. Okay, let's try to solve this question. It's a direct question because everything is given to me. In fact, finding the radius is the most simplest thing which you can do, which will be mv sine theta divided by charge into field. Mass is 2 grams, so 2 into 10 to the power minus 3 kgs. Speed 10 to the power 2. Sine 37. Sine 37 is 3 by 5. Whole thing divided by. Charge 4 micro. 4 into 10 to the power minus 6. Magnetic field 10 to the power minus 2. So let's see what do we get. 2 and 4 cancels. 2 and 4 cancels, becomes 2. 2 into 5 is basically 10. Okay. Now this 10 goes with this, becomes 10 to the power minus 1. Okay. So take these things up and see what do you exactly get. So only the number 3 is remaining. 10 to the power minus 3 and 2 will make it minus 1. Minus 6 and minus 1 will make it minus 7. So take it on the top, 7 minus 1 is 6. So 3 into 10 to the power 6 meters, that's a huge radius. So that's the radius that you will get for this particular values. Actually the values that I've chosen are maybe not that great. That's why I'm getting such a huge radius. But that's okay. Everyone fine till this point? Everybody fine till this point? Let's go ahead and try to find out the pitch. Now pitch, if you remember, is axial speed, which is v cos theta multiplied by the time period, which is 2 pi m divided by qb. Velocity is 10 to the power 2. Cos 37, 4 by 5. 2 as it is, pi as it is, mass 2 10 to the power minus 3 kgs, whole thing divided by 4 10 to the power minus 6, magnetic field 10 to the power minus 2. All right, let's see what and all get cancelled over here. This 4 and this 4 obviously gone. Yeah, this 2 and 2 will make it 4. So definitely I have the number 4 and the number 5 as well as the number pi over here multiplied by 10 to the power 2 and 10 to the power minus 3 will make it 10 to the power minus 1 on the top. Minus 6 and minus 2 will make it 10 to the power minus 8, which will make it 4 pi by 5. Take this on the top, it will become 8. 8 minus 1 is 7. So 10 to the power 7 meters. So that is the pitch. So it is going in a big circle with a large pitch. Okay. Now, usually such things happen when solar flares occurs. So you know solar flares, suddenly the sun burns a lot and some places suddenly there is a huge explosion because of lot of fusion happening. So there is a sudden discharge of lot of charged and all random particles and they go spread all across our solar system. Once these charged particles enter the Earth atmosphere, remember Earth has its own magnetic field. So the Earth's magnetic field applies magnetic force on such charged particles and they go in nice helical paths because the charged particles are not coming at 90 degrees, they are coming at some angles. So you will see these charged particles go in such nice large helical paths and in this due process they produce this aurora borealis which looks very nice in the night sky. They lighten up the sky with green, bluish, violetish colors because they interact with the Earth's atmosphere, they ionize and you will see these beautiful colors when solar flares occur and these charged particles enter the magnetic fields. These magnetic fields are very strong at the poles, that's why you see them in the polar regions, not in the tropical regions. Is that okay? Yes. Yes, Kane Bharat Kem, that will be sufficient for your mains preparation. No worries. You can watch those videos as well. Great. Now there was a very interesting question. Which came and it looked something like this. There is a gun which throws out charged particles at some small angles but with the same speeds. U. The angle is very small. The angle of projection is given to be small. It is known that all these charged particles again meet somewhere, somehow after some time. Because they are diverging, this angle of projection is very small, they again converge over here. This is the point of first convergence because they meet over here for the first time. Again they diverge and again they meet. That's okay. But the question is, see, if you consider in terms of ray optics, light, a divergent beam is converging, it feels like there is a convex lens, some focal length, etc. So the question is basically find this distance find the focusing distance. Find that focusing distance given that the magnetic field is in this direction. Given that the magnetic field was everywhere over here, it was like this. The magnetic field was like this in this direction. Okay, that's the question for all of you. And these charged particles, these charges were each having charge q and mass m when they were thrown from that gun. Very nice question. Think about it for a moment. Why the hell will they converge? Why the hell will they converge? Why we don't use v sine theta? Because, where did it go? Pitch means you're going along the axis, so you have to use v cos theta. That speed into the time. I'm going with the constant speed. So in one time period, how much did I move ahead? So that's why v cos theta. How much did I move ahead? This distance will matter on this x-axis speed. That's why the axial speed, which is v cos theta, not v sin theta. Is that okay? All right. Let's see if you guys can figure this out. I'll tell you, if you take any charged particle, let's say the velocity is like this, and it's making some small angle with the magnetic field, how will the motion be, guys? How would the motion be? Would it be helical? So won't it look something like this probably? It will be basically a helical motion, guys. And there are many such charged particles, so there will be many such helices. I hope you guys understand it, because there are many such charged particles. So definitely there would be many such helical motions which will be occurring at the same time. Great. Then you'll be like, sir, their motion is so ridiculous. How do I even figure out where they focus? No worries. See, the angle which they make is very small. That is probably the hint now. You take any helix. After one revolution, it moves ahead exactly ahead by the distance called as the pitch. And it's exactly in front of it. Now that pitch is given by velocities cos theta into 2 pi m divided by charge into magnetic field. Since the angle of projection is small, that means theta is small. And for small theta, what is cos theta approximately? Isn't it 1? So if cos theta is 1, that means the pitch is the same for all. Therefore, the pitch is almost same approximately for all of them. That means some other charged particle might be thrown at some other angle, but roughly speaking, after that revolution, probably it comes almost back over here. Right? Is that making sense, guys? To all of you? Some other charged particle might be going over here, might be going like this, and maybe just landing over here. Their pitches are roughly the same, angles are different. And cos theta being 1 makes that happen. So where they meet is exactly that point of focus. So this is the point of your focus. Hence that pitch must be your focal point. So the focus is basically the pitch. Hence it is nothing but V into 2 pi m divided by charge into field. That is the question's answer. This question had come in JEE Advanced. People thought it is some crazy ray optics question, but actually the answer was so laddu. The concept was the same. Sakil, yes, you can watch it for the NEET exam, but slightly little bit more advanced, not little, more advanced only. You can watch my NEET lectures also on the Vedantu NEET English channel. It's up to you, but yeah, definitely there is no harm. It won't do you harm. Yeah. I'm so glad you found me keen, and I hope that this relationship continues till and even beyond you get your engineering or dream college. Okay? Cool. So now that you have understood this question, let's do another special case where you have something called as the crossed field, and this is very interesting thing. In this case, what happens is, let's say you have, let's do one thing first. You have magnetic field in a certain region. And then you have a charged particle which enters that magnetic field with some velocity. We know that velocity is here, magnetic field is inside, V cross B will be upwards. So there will be a magnetic force on it in this direction. And that will be nothing but QVB. Sin 90 is 1. Now, I want that the charged particle should not deflect only. That means the path taken by it, should be a straight line. I want that to happen. So basically, no deflection should happen. You will be like, sir, how can that be possible? Because there is a force. So I will introduce another force in the exact opposite direction, and that will be like this. But that will be the electric force which is charged into the electric field. So you might wonder, where is the electric field now? So the electric field is basically like this. So our electric field is basically like this. So this is your electric field. So if I adjust the electric and the magnetic field properly, these two forces will cancel. There will be no deflection. So for no deflection scenario, okay, 100% I can say that the magnetic force balances the electric force. Magnetic force being QVB, electric force being charge into electric field. QQ cancels, the velocity comes out as E divided by B. Now this is a very important result. This is called crossed field because here, if you notice carefully, the velocity is perpendicular to the magnetic field, and that is in turn perpendicular to the electric field. In fact, all three are mutually perpendicular to each other. Magnetic field is inside, velocity is here, electric field is down. So all three are mutually perpendicular. That is why it is called as a crossed field. Cross is perpendicular, but here all the fields are crossed perpendicular, including the motion. In such a scenario, if you throw the object with this speed, then it will go undeflected. Very important. It will go undeflected. I hope this is absolutely clear for everyone. Till this point, clear, my dear students? Yep. Now, you might be wondering, sir, what would happen if my velocity is not equal to E by B? In such a case, you will see that the path taken will be either like this, or it could be like this, depending on whether the speed is more or less. Imagine now, I have many charged particles with different speeds, I have an obstruction here with a small hole in that. Only those particles with a speed equal to E by B will pass through that hole without any deflection. Everything else will hit that obstruction. So, by adjusting E and B values, getting a speed, I can carefully allow only those charges with a certain speed. So, I make a calculated choice of which particles will go out of that hole undeflected. So that's why this is also the principle of a device called as velocity selector. Out of all the speeds, I select a peculiar speed using this formula. Okay, I hope this is clear. So this is the concept. This is the concept of something called as velocity selector. Velocity selector. Very, very important. Absolutely clear, my dear students? Till this point? Absolutely clear? What is the concept of this velocity selector? I just probably give you a question on this. In a crossed field, a charge of 5 millicoulomb passes undeflected in 0.2 Tesla magnetic field and an electric field generated by K, or let's say X volts across 2 meters. Question is find X. Question is basically find that value of X. You might be wondering what the hell is happening here. Don't worry. So there is a charged particle and I want to pass it undeflected in this thing. Electric field. Oh, sorry. I forgot one thing though. The speed. With 20 meters per second. That is what is given to me. With 20 meters per second. Alright. So how do we do this particular problem? First of all, if it is going undeflected, 100% the velocity will be electric field by magnetic field. So electric field must be V into B. Velocity is 20. Magnetic field is 0.2. The decimal shift, so it should be 4 volts per meter. In fact, the unit only should give you away the answer. Electric field is voltage applied per meter. So remember, it is voltage difference per unit length, delta V by delta R, that is 4. So delta V will be 4 into delta R. The distance is 2, hence it should be 8 volts. If you are wondering where this 8 volts is applied, basically you take a plate here, and you take another plate over here. This will be the negative plate, this will be the positive plate. So there is a potential difference which is being applied. There is a potential difference of 8 volts which is being applied across 2 meters. That's what will create the field and that's what will basically make it undeflected. Is that clear now how this is done? Shall we go ahead to the next concept? Guys? Ready for it? Okay. Cool. Now that we have studied that magnetic field applies force on moving charges, Then just imagine there is a wire. Imagine there is a wire. There is a wire which carries some current. There is a wire which carries some current. We know that inside of it, definitely there are charges. There are definitely charges, and these charges will be in motion. So therefore, there are charges in motion. Now, if somebody applies a magnetic field, somebody applies a magnetic field on them, okay, somebody applies a magnetic field on them, won't those charges get pulled or pushed because of this force? Indirectly, those charges will end up pulling the nucleus. Indirectly, basically the entire atoms and the molecules, which means the wire itself will experience force. So therefore, you will probably see there will be a force acting on the wire. Force on the wire. So hence, a current carrying wire, therefore I can say, therefore a current carrying wire in a magnetic field, in a magnetic field may experience a force, may experience a force. Why the word may? Because just like QV cross B can be 0, same way this force also can be 0. That's why I'm saying maybe it can experience a force. Who gave the magnetic field? The magnetic field can come from some other magnet or some moving charge. Current carrying wire produces magnetic field. So this is an external magnetic field, not the magnetic field by the wire. Be careful, the own field can't apply a force. This magnetic field is because of some other particle or wire, not the same wire. Okay, because that own wire will create its own magnetic field, but that can't apply a force on itself. That will be wrong. Just like a charge will create its field, but that field can't apply a force on that charge itself. It can apply a force on some other charge. So a magnetic field and a wire carrying current can experience a force, and the value of that force and the value of that particular force is given by IL cross B. But usually the wire may not be straight, it might be bent. So you take a small element, and on that small element you find a small force acting on it. Maybe it's a small force dF. It's a small force called dF. So this is the small force on an element. This is our element. This is on the element of current, on the element carrying current. Okay, you can find that small force acting on it. So if you want to find the total force on the wire, there will be many such teeny mini dF forces in different directions. You do addition, that means integration. So that will give you the total force. So the total force on that particular wire will be just integration of all these dFs. That means it will be just nothing but you take that current outside, integrate dl cross the particular magnetic field. Maybe the magnetic field was here or there, I don't know. Cross the magnetic field. So that will give you the total force on the wire. You obviously have to integrate it, because all the forces can be different magnitudes, different directions. Till this point, is it clear why we need to integrate? But otherwise it is I length cross B. Again, cross product rule is involved. Cross product rule is involved. Now, what happens is, if the wire is a straight line, then you don't have to worry about it. Then instead of integration, you can just say IL cross B. Instead of I dl cross B, you can just say the total force on that straight wire is IL cross B. If the angle between them is theta, then it will be ILB sine theta. Very simple. Let's take some examples so that you guys understand this. Imagine there is a wire carrying 2 ampere current like this, carrying 3 ampere current like this, carrying 4 ampere current like this, carrying 5 ampere current like this, and the magnetic fields are as follows. Magnetic field is 10 Tesla over here. Here it is 5 Tesla. Here it is, let's say, 3 Tesla. And here, let's say, it is 2 Tesla, making angle 30 degrees. In each case, can you figure out the force and its magnitude? In each case, can you figure out the force as well as the magnitude, assuming all these lengths, all are given to be, all the lengths are given to be 2 meters. All the lengths are 2 meters. Let's try to do this problem, guys. Here, the angle between length and magnetic field is 90 degree. So the force magnitude will be current into length into magnetic field. To do the force, so it will be 40 Newton in this case. But direction wise, length is up, magnetic field is right. Length cross B, it will go inside. So the force will be directed inwards. Force will be directed inwards. In this case, the angle between length and the magnetic field is 180. So sine of 180 is basically 0. So the force is also 0. So no force in this case. Either it is parallel or anti-parallel, gone. In this case, there will be, in fact, the angle is 90 degree. So the force will be ILB, current is 4, length is 2, magnetic field is 3, sine of 90. Okay. So ILB into sine theta. 4 2s are 8, 8 3s are 24. So 24 Newton. Length is up, magnetic field is left, so it comes towards you. So this force is directed out of the plane of the board. So the force on this wire will be coming towards you. Is this clear, everyone? Okay. Next, over here, if you notice, force will be current, which is 5, length 2, magnetic field 2, into sine of 30, angle between length and magnetic field. So sine 30 is half, 2 cancels, so 5 2s are 10, so 10 Newton. But direction, length cross B, length is down, magnetic field is there, so length cross B makes the thumb come towards you, so out of the plane of the board. So that's how you find the force on a current carrying wire. That's how you find the force on the current carrying wire. Kamalakshan, I'll be coming to the torque part in a bit. First we are doing the forces, then we'll go to the torque. Hold on for that. Okay. Now, if that is the scenario, imagine you have a curved wire and you have to find the force. Usually it would be very difficult. Imagine there is a curved wire carrying some current like this. Okay, carrying some current like this between these 2 points, and you have to find the force on it. Maybe the magnetic field is like this, who knows? This is the magnetic field. It so happens that the force on a curved wire in an uniform magnetic field comes out to be, if you just draw a straight line joining the start and the end, producing the same current, you will see it will be exactly equal to the force on a straight wire, between the ends. This is a very, very important statement. This is the equivalent length. This is the effective length basically. So I can say the force on a curved wire will be nothing but the force on the straight wire, which is nothing but current into the effective length cross the magnetic field. But this magnetic field has to be constant, else it will not work. So this is the force on the curved wire. Is this absolutely clear, everyone? Very, very important statement. Rather, I would say block this off. Force on a curved wire in a uniform field is force on a straight wire, effective length connecting the ends. Now, what are the implications of this? So there are so many problems which can come out of this. Imagine you have a loop of current in an uniform field, in an uniform magnetic field. A loop of current means the current will go back and come to the same point. That is basically a loop. Imagine such a loop is placed in some magnetic field, uniform magnetic field, of course. Uniform magnetic field. Can you tell me what is the start and what is the end? Because a curved wire, I will convert it into a straight wire. It starts from a point and ends at that point. So won't the effective length itself be zero? If that is the case, the force on that loop will also be a big fat zero. So a loop of current inside a uniform field will never ever experience a net force. Remember, this is always the net force. So the net force on that loop will be a big fat zero. In fact, don't even think of it like an example. Think of it like a property. Yeah. Yes, we'll be doing advanced PYQs as well very soon. Yeah. First, let's complete the portions as well. Correct. Now, there was a beautiful problem which I saw based out of this concept, and that looks something like this. A circular loop of radius r, current I is placed in a magnetic field perpendicular to its plane. Find the tension in the loop. Find the tension, in the particular loop. At first, it looks like what the hell is happening, but with little bit of analysis, you understand, okay, this is what was happening. So let's just imagine that loop first. This is that loop which carries some current, and there is magnetic field perpendicular to it. So let's just say this is how it looks like. This is the magnetic field. Okay. So let's say this is the current in that particular loop like this. Now you might be wondering, why the hell will there be tension in that loop? Okay, no issues. Do one thing. You just take this part of the loop, just this left part, and as the current goes like this, for this particular element carrying this current, magnetic field is inside. Where is the force? Length cross B, I think the force is this way. This is the small df force. Now on that entire loop, just think about it, on that particular entire loop, there is magnetic force which is going to pull it from every angle. From every angle, it is going to get pulled like this. So it will definitely be pulled outward, and because it is pulled outward, that particular loop tries to expand And in this process, what happens is the loop is under tension. The loop is under tension. That's how tension comes. Imagine you are trying to expand the loop from every possible direction. So there will be tension in the loop. That becomes now interesting to solve. So like, sir, will there be derivatives and integration involved? Well, you can do it like that, but I feel there is no need of it. Just consider half of that loop. Just consider half of that particular loop. That half of that loop, because it is experiencing magnetic force in every possible way, the net force on that half of that loop can be found out by considering an equivalent loop, which is basically a straight line of length 2r, and on that, what will be the force? On that, what will be the force? So that force will be current into distance, which is 2r, into the magnetic field. So that is the net force on the semicircular loop or the semicircle. Why did I take the semicircle? I'm trying to draw the FBD. Due to magnetism, the force is I2RB, but at the same time, do not forget the loop is under tension and tension acts everywhere throughout the loop. So this point will experience a tension this way, and this point will experience a tension, a pull like this. Every point experiences a pull. So this force of T plus T should be exactly balanced by this upward force, which is 2IRB. So therefore, 2 times of tension is 2IRB. Therefore, tension is just IR into B. So that's the tension in the loop. So using this simplification by taking a curved wire into a straight wire, this problem becomes so easy. The semicircle experiences the same force as the straight wire, which is having a length of 2r, which is the diameter. So that force will be balanced by the tension. The tension will be there throughout the loop. Remember that. Tension will be there throughout that particular loop. Everywhere it is there. That's why you can take any 2 points, tension is same, and show the tension, balance it. That's all. Is it clear, everyone? Loved this question? Can we go ahead? Loved this particular question? Shall we go ahead to the next one? Okay. Now, imagine two wires perpendicular to each other carrying two currents. This is carrying current I1, this is carrying current I2. What do you think they will do to each other? Nothing else is there. That's it. Wire carrying currents influencing each other. How will they do that? Let's see. Now each wire, we know, creates its own magnetic field. If each wire creates its own magnetic field, that magnetic field can affect the other wire. Okay. So if I take this wire, which is carrying current like this, the magnetic field due to that can be found by right hand rule. Place your thumb in the direction of the current, the magnetic field lines go like this. So you will see that the magnetic field lines are basically in this particular manner. But as you go far away, the field will reduce. This is your magnetic field, which reduces as you go far away. So if you're on this side of this particular wire going up, the magnetic field will be going inside over here. Their intensity gradually reduces. Here it will come towards you. Here it will come towards you. And as you go far away, the intensity reduces. That's how it will look. Here it is strong. Here it becomes weak. Now, just look at this horizontal wire. It is getting influenced by this magnetic field. The wire's length is along the right hand side. Magnetic field is inside. So length is there, magnetic field is here, length cross B goes up. So the force on this wire will be up, but here the field is strong. So the forces here on the elements will be stronger. But as you go far away, you will see that the forces become smaller and smaller. Same logic you apply here, the force will be exactly opposite. They will be like this. But as you go far and far away, the forces become smaller. Exact symmetry is there. So if you find the force on the other wire, the net one, won't it be a big fat 0, guys? As many forces up, that many forces down of the same amount. Definitely they should cancel. But there is a problem over here, and I hope you have seen it. Each force forms like a couple force. A couple force is where you have equal and opposite forces separated by a distance. It produces torque. So therefore, you will see that the net torque will be there like this. The net torque is definitely not 0, and it is in the anti-clockwise direction. So this particular wire will rotate but not translate. It will have torque but no net force. Acceleration will be 0, but angular acceleration will be there. Isn't it an interesting question? Yep, everybody with me? Clearo? Cool? This is how wires carrying current can influence each other. Now, these two wires were perpendicular, but what if they were parallel to each other, carrying currents in same or in opposite direction? So say for example, you had a wire like this carrying some current I1 and some another wire carrying current I2. We know each wire produces its own magnetic field. So this wire, hold your thumb in the direction of the current, the magnetic field will be like this. The magnetic field will be like this due to that particular wire. That magnetic field, when it reaches this wire, will obviously be like this in this direction. This is field due to current number 1. Clearly, it is perpendicular. You can see. Now, there will be a force on that wire. Length is here, magnetic field is down. Length cross B makes it go like that. So the force must be like this. I'll have to visualize this now. Okay, try to visualize this. The force will be in this direction on wire 2. So the force on wire number 2 will be current of that wire, which is I2, into length of that wire into the magnetic field due to that first wire. Which is given by mu naught current into mu naught I divided by 2 pi distance between them. So there could be some distance between them. So let's call it as d. So mu naught I by 2 pi d is the formula for the magnetic field. So keeping these terms as it is, now shifting that length below, what I get is the force per unit length. So the force per unit length, how much will it be? You will have mu naught I1 I2 divided by 2 pi d. This is again a very important formula. Force between two parallel wires carrying currents is mu naught I1 I2 by 2 pi d. This is per unit length. Yep. So now, if the wires are carrying currents in the same direction, same attracts. So if they were going in the opposite directions, they will repel. So same direction there will be attraction, opposite direction there will be repulsion. This is something which you have to remember. Is that okay? Everyone with me on this? Clear? And the magnitude of it. You can get into Stanford University. Definitely, you need to write SAT. You need to have good scores. You need to have extracurriculars. You need to have some great SOP and recommendations. And obviously, if you cannot afford the scholarship, then you should be able to afford the high fees as well. But again, they should accept it. All right. So, Omasari, you are in 11th, I believe. And you are from Kerala. And I need some motivation because I'm down now. So, Umasari, I'm not sure why you are down. It could be a variety of reasons, maybe because of backlogs or maybe something wrong with your surroundings, or I don't know. Number one, stay around positive people. Friends who want to study for IIT, friends who want to crack and do something much better than usual masses, because 90 to 99% crowd around you will be doing the average things. There will be very few students who want to do extraordinary things. So surround yourself with extraordinary people. Number two, be patient and consistent. So these are the two tents that you should, have in your house. Persist, you should be very consistent, right? So make sure that you are very, very consistent and you do not give up so easily, and you are patient, meaning if something does not go wrong, if something goes wrong, do not be like, oh, I cannot do well. Mock test went down, scores went down. It's okay. Next time I will do better. And slowly keep studying. You can't do 30 chapters in 1 week or 1 month. You can't do all the backlogs in 1 week or 2 weeks. Set a nice practical deadline and slowly, today I did 1, today I did 1.5, next I did 2, 2.5, 3, and slowly you will see within no time you would have reached. And most important thing is practice, practice, practice. That's it. That's something which every JEE aspirant should do. Do that. I'm pretty sure you will be able to overcome that. Okay? Right. Now that we have seen forces acting on current carrying wires. Okay. And I saw that in loops, at least the force was 0, but the torque may or may not be 0. Look at this. Where did we go? The force acting on a current carrying loop was 0, but the torque may or may not be 0. So for understanding that concept, here is what I will do. Let me take a loop of current. If this is a loop of current, and let's say this is that area, this is that area of that particular loop over here, like this. Then any loop carrying current, what does it behave like? Is a magnetic dipole, meaning it behaves like a magnet. So definitely there will be magnetic polarities, north south. If the current carrying is like this, you draw a vector perpendicular to that. You draw a vector perpendicular to that area that represents your magnetic dipole moment. That represents your magnetic dipole moment, which is given by number of turns into the current into the area vector. So that is your magnetic dipole moment. Now, if such a thing is placed in external magnetic field, is in somebody else's, so external magnetic field, just imagine this now, there is some magnetic field like this. What happens? Well, there is no net force, but there is definitely a net torque on it. Definitely there is a net torque on it. So if I pass some magnetic field, if I just imagine there is some magnetic field over here like this, there is some magnetic field over here like this, definitely it encounters a torque. That torque always tries to align the magnetic moment towards the field, no matter where it is. So that torque always tries to align the magnetic moment in the direction of the field, and that torque is given by magnetic moment crossed with magnetic field. Magnetic moment crossed with magnetic field. This is the torque acting on it. This formula is very similar, or in fact it has been obtained from the torque on an electric dipole. Torque on an electric dipole was P cross E. Here instead of P you have M, instead of E you have B. Electric replaced with magnetic field, electric moment replaced with magnetic moment. So that's the torque, but obviously the net force is zero, something which you should remember. And we saw that before also, any loop carrying current never experiences net force, but it can experience net torque, and this is the formula for the net torque. Is that clear? Yep. Oh, no problem, Yashwant. You are watching all the sessions after live, but I'm guessing that recordings also play a very important role, because you can choose your own pace, your own convenience in case you are not able to attend live, and that's okay as long as you are consistent and watching the recordings. And hopefully that Yashwant, I'll be seeing you on the other side next year in the best of the best colleges. Yes, Omasari, definitely we can help you a lot. So there are different things. Now it depends whether you are in the coaching already or not. Are you doing self-study or not? Is your preparation that well or not? Do you think your methods will help you, or do you need, me or my team helping you out, or you just want suggestions and that's about it? So depending on that, we can proceed. Remember, there is also electrical potential energy which was given by minus P dot E. Here you have magnetic potential energy. Here you will have magnetic. Here you will also have something called as the magnetic potential energy. U, instead of cross product, it will be a dot product of the magnetic moment with the magnetic field. So this formula also very important. Now, based on these things, we can study how different orientations play different roles and different importance in our understanding. Let's take some different scenarios. Say for example, this is our loop. Okay, I have shown some different orientations over here. Basically, theta is 0 between magnetic moment and field. Here, theta is 90 degrees. Here, basically, theta is 180 degrees. Pink line being the magnetic moment, and the green ones are the magnetic field. So we know torque is mb sine theta, and the torque will always try to bring the magnetic moment towards the field. So it will be mb sine theta. Even here, this magnetic moment will try to bring the field will try to bring the magnetic moment in this direction, like this. Always tries to bring it over there, and energy will depend again on the orientation. So in this case, theta is 0, so sine 0 is 0. So can you see that the torque is 0, force was anyway 0. Here sine 180 is 0, so again the torque is 0. Whenever force and torque both are 0, so it is the case of basically equilibrium. This is definitely equilibrium. Here the torque is not 0. Here also torque is there. This is also equilibrium. Equilibrium. I hope this is absolutely clear. In this case, if you measure the torque, sine 90 will be 1. It will be mb. In fact, this will be the maximum torque which can happen when it is perpendicular. Now, if you look at the potential energies in every scenario, in this case, potential energy generally will be minus mb cos theta. Cos 0 will be 1, so it will just become minus mb. So the potential energy will be minus mb. Here, if you measure the potential energy, theta is 90, cos 90 is 0, so potential energy will be 0 joules. Here, if you put theta as 180, cos 180 is negative 1, negative into negative positive, so potential energy will be positive mb. Now when the energy is more, that equilibrium will be which kind of equilibrium? 100% it will be unstable equilibrium. When the energy is minimum, that equilibrium will obviously be stable equilibrium. Which means if you take this loop and move it slightly, it will come back here. You move it slightly, the torque will pull it back here. It is a stable equilibrium. Whereas in this scenario, you will see if you displace the loop slightly, that's it. The torque will bring it back here. So it is unstable. It's just made to stay there under careful conditions. If you slightly move it here or there, zoop, the torque will pull it back over here. So that's why unstable, more energy, stable will have less energy. Is that clear? Rachkan, these are good lectures for JEE Mains and Advanced Basics. After this, you have to solve lot of questions and PYQs. So I am taking up 2024 PYQ sessions to make sure you are at mains levels, and then we'll be also doing practice sessions once the syllabus is done. But I need your support. Guys, if I see again you guys have become very lenient, I will stop the series. I am telling you now only. I will not take so much of pain if you guys are not very consistent. So I want to make sure that you guys too are consistent. Even if you are watching recordings, it's perfectly fine. No issues at all. But watch the classes, take full benefit, because then only we can start with the proper revision, mock tests, advanced questions, exclusive sessions for sure shot, exclusive sessions for different varieties of non-PYQs, NTA based questions, everything. Cool? Omasari, everyone? Yes. Yeah. Right. So, yeah, you need the classes. There are multiple ways through which you can take up my classes, and my recorded versions also are there. So I'll tell you, you can do one thing. Just check this out on the channel. Vedantu Pro batch. Okay, this is the last JEE batch. In that, you will also get my recorded classes plus the live classes from other teachers too. So there is a form link over here. Just click on that particular link and just get in touch. and tell them that you want VBuddy. VBuddy has my classes, which is a part of this, and you also get live batch for all the 3 subjects, and they will also offer you discounts because now Mega Vedantu scholarship admission test is there. So this is the best time to actually negotiate and get maximum scholarship. So that is a cheat code which I am telling you. Okay, so for you to get the best of the best offers right now. Okay, so it's there even in our current video also, Vedantu Pro batch. So you can just search in the videos part. In the videos part, you will get it. Okay, it's there recently only. Yeah. Yep. Thank you, Rachkan. Thank you. Great. Now we can solve some questions based out of this. Okay, because that is the final part of this lecture. A loop carrying 0.5 amperes having 10 turns and area 0.1 meter square is placed in stable condition under 0.4 Tesla field. If actually rotated by 180 degrees, find the work done externally to do so, because it goes from stable to unstable. Also, find the maximum torque on it in the process. Find the maximum torque which can act on it during that particular process. That's the question. Let's try to solve this now. Let's try to solve this particular question. Now, even if you have an average mindset, let me tell you, many of my average students have cracked not mains, advanced. So they thought that they were average, but later on they only came and told me, sir, thank God, you thought that I was not average, but something miraculous happened in 3 to 4 months, and after that they cleared mains, and again in the remaining months they prepared for advanced, and now they are doing extremely well and happy in their IITs. So you feel that you are average until you start studying under our guidance. Number 1. Okay. Number 2, don't feel low about yourself. There is a lot of things that you can do in the last few months. So please work on it and take as much help as you want. Okay. Great. Cengage is okay for advanced. I mean, not the best so one, but okay. I mean, not bad, not great. All right. So how do we do this? If you want to find the work done externally, it's always the change in the electrical, magnetic or whatever potential energy. So energy when it is at 180 degrees final minus energy when it is at 0 degree. When it is at when it is at 180 degree, I just told this to you, for 180 degree, energy is MB. For 0, it is negative MB, basically using MB cos theta formula. So basically it will be MB minus, this will be minus MB. So basically it will be 2 times MB. But what is M? It is number of turns into current into area. That is the formula for magnetic moment of a loop carrying current. In case you've forgotten about it, I just written it over here. Okay, we did this in the previous lecture also. It's not like this is new. This we have done it in the previous lecture only. So NIA. So great. So I now know everything over here. 2 times number of turns 10, current 0.5, area 0.1 into B. Where is B? 0.4. Okay. So what will this become? 10 into 0.5 will make it 5. Okay, 5 into 2 will make it 10. 10 into 0.1 will make it 1. 1 into 0.4 will just make it 0.4. So the answer is 0.4 joules is the external work done. That's sorted. Let's go to the second part. Let's find out the maximum torque. Maximum torque happens when the angle is 90 degree. So MB sine 90. So magnetic moment is N, I, A, B, sine 90 is 1. Number of turns 10, current 0.5, area 0.1, magnetic field is 0.4. Okay. 0.5 into 10, 5. 5 into 0.1, 0.5 again. 0.5 into 0.4, well, that's basically 5 fours are 20, shift 2 decimals, so it will be basically 0.2. So 0.2 Newton meter is the maximum torque during that particular process. Is that right, everyone? I hope this is clear. Cool. Shall we go ahead? Okay, to the next question coming up on your screen. Now, this question is also very interesting. Let's see if we can do it. Question is, find the net force and the net torque on the loop due to the infinitely long wire as shown. Due to the infinitely long wire as shown. So here you have a square loop of side equals to A and carrying current of I, and then you have another wire over here. This is carrying a current of 2I. This is obviously infinitely long. This is infinitely long. Other things which are given to you over here, this distance is also A only. This distance is also A only. Okay, now you have to figure out what are the net forces and the net torque acting on the loop. Let's try to solve this. Now this long wire which is carrying current will obviously create its own magnetic field. Hold the thumb in the direction of the current, the field will be like this. So it will go in front of you and then behind from the right side, and it will come like this. So it is going inside over here. As you go far away, the field will reduce. So 100% the field is much stronger over here as compared to when you reach on this side. So the field is very strong and it becomes weak. This will affect the force acting on each side as well. Be careful. For example, on this side, if the current is going like this, I think that should have been given in the question. If it was not given, I will give it over here. Okay. Current is going like this. On this side, length is up, magnetic field is inside. Length cross B will make the thumb go towards the left side. So the force on that part will be over here. Same thing on this side, the field is weak, length is below, length cross B will make the thumb go there. So the force will be towards the right, but of a smaller magnitude. This is the force towards the left, this is the force towards the right. Obviously this will be more than this because field is strong, here it is weak. Making sense, everyone? Cool. What about this part? Well, on this part, the field is continuously changing. Okay. Length is right side. The length of the wire should be taken right side. Length cross B will make the thumb go up, which means the forces are of varying magnitudes. Here it is more, then it is less and less and less. Same thing here. Here it is less, here it is more, and it keeps slowly, gradually reducing. But the best part, every force has an equal force in the opposite direction on the other side. So they end up cancelling out each other without any torque. Without any torque. Why? Because this force is along the same line as this force. Whenever two forces are along the same line, the torque produced by it will be zero. But if one force is here, one force is here, there is some separation, clearly there will be a torque. Then the torque won't be zero. So because they are along the same lines, the torque will not be produced only. Next thing, even these two forces are along the same line. So no torque because of this. No torque because of this, because they are collinear. Therefore, the net torque in this situation will be zero for sure. But force we have to figure out. Torque is at least not there. Rachkan, 3 months, is it enough or not? That depends on how much hard work you are putting in and from where you are starting, how much time you are spending. If you say that, sir, I will only study for 4 hours and I can do only so much, I feel that maybe I will do it, then it will not be possible. But you will be like, no, sir, I will study for 8 to 10 hours. If possible, I'll bunk school, I'll study for 12 hours also. I'll sleep for 3-4 hours or 5 hours on few days, but usually I will sleep an average of 6 hours. Sir, I will try to solve all mains questions. I will not focus much on advanced, sir. Sir, I will complete at least 80% to 90% of the syllabus and main focus on high weightage. Then 99 percentile is 100% possible. Okay, mark my words. Yeah, and I'm so glad, Sovan, my previous series have been useful. The same thing I plan to do with this. I know in 2027, 2028 and maybe in 2050 also, somebody watches these classes, they are going to find it useful for JEE, assuming syllabus is constant. Okay, now about the force. See, the net force will be the force towards the left minus force towards the right. Force is ILB, current is the same. The current is basically this I into the length is basically A, into magnetic field at that point minus current into A into magnetic field on the right hand side. So current and A are common. I am just left with BL minus BR. What is magnetic field on this particular segment? I am at distance of A. Field formula is mu naught into the current, which is 2I, divided by 2 pi distance. Distance is basically A. Minus magnetic field over here, the distance is 2A. So mu naught 2I, because this current is 2I, divided by 2 pi into 2A. What will happen? 2 cancels, 2 cancels. 1 minus 1 by 2 is 1 by 2. So this will just become mu naught I, 2 has cancelled, by pi A, and this will be 2 because that half will come. That's what it will be. And from here I have again IA over here. A and A will cancel. I into I is I square. So mu naught I square divided by 2 pi. Mu naught I square divided by 2 pi. Yep, A has got cancelled. So that is your net force, guys. That is your net force. And this is towards the left. This is towards the left side. That is the answer. Is that clear, everyone? Shall we go ahead? Yep. Is it absolutely clear? Very good. Excellent. Excellent. Now there is one more beautiful question which I would like to solve. This would be the last question that we'll be solving today. Are you ready for it? Full of energy? If yes, we'll solve. If no, then we'll stop. I feel this is a good question. Shall we solve it? Okay, let's do this. Let's do this. Madhavraj, if you're solved Tatva and you are doing PYQs and also non-PYQs and also solved examples and also attending the classes, 100% you will get NIT 3G. You will definitely get. But properly solve it. Don't solve it for the sake of solving. Sir, I completed 100 problems. No use. But are you analyzing how you did it? Are you seeing? Don't put timer. It's okay. You take even 5 hours or 10 hours. But analyze. See why it was like that. Maybe answer is correct, solution is wrong. Do it properly. 100% I'm telling you, Tatva book mastering, the DPPs which we are giving, also the video lectures which are there on the channel, old videos, anything, even the new videos, definitely will be in 3G. Okay? And yeah, I hope that is okay. Madhavraj. Hi Samarth. Let's do this question. There are 2 rails, okay, 2 rails like this. And on those 2 rails, a rod can slide. A rod can basically slide on them. But it is held at rest because of the magnetic field. So find the current which will keep the rod at rest. That is the question. Now, first of all, when you look at this question, it looks very easy, but there are few things which you need to be careful about. I feel the best way to solve the problem is looking at the side view of it. So the side view of it looks like this. This is the rail. This is probably the rod. The rod will look like a dot because it is going inside out. The magnetic field is going up like this. Okay, magnetic field is going up like this. At the same time, there are multiple forces acting on the rod. Like there is obviously a normal force. There is obviously a mg force, and that mg will obviously have 2 components, one here and one here. So what are those components? One is obviously mg sine theta. This is normal. This is mg cos theta. Now it is clearly mentioned that the rod is at rest. So if it is going to be at rest, all the forces must cancel each other out. So normal balances mg cos. Okay. Who is balancing mg sine? Who is balancing mg sine? That means there must be force of magnetism which is up the plane, at least a component of it. Only then it can stay balanced. Oh, so the current carrying rod because of the field experiences ILB force. The rod is like this. Magnetic field is upwards. If I do length cross B, that means the current is coming towards you and magnetic field is upwards. Length cross B makes the force go this way, which won't keep the rod at rest. If the current is going inwards, then probably things can be different. Imagine the current is inwards. Length is inwards. Length cross B will make the force go this way. Hence, imagine ILB force. Hence, imagine your ILB force is like this. I length B. Oh, now things start making sense. This ILB will now further have 2 components. One component here and the other component like this. And the other component like this. This component will be ILB because this will be theta. It will be ILB cos theta. This would be ILB sin theta. 100% the normal force will balance mg cos theta plus ILB sin theta. This will balance it. In this direction, these two will balance. Mg sin theta will balance ILB cos theta. But I want the current, right? Therefore, current will be mg divided by LB. Sin by cos is nothing but tan. So, tan theta. So, this is the current which will keep the rod balanced. And the direction of the current, it's inside the plane. That means if I look from here, so the current goes like this, like this, like this, and like this. This is how the current should go so that it stays there. If it goes other way, then it will not slide. In fact, it will end up accelerating. Okay, everyone? Loved the question? Isn't it a very nice question? Clearo, amazingo. Sir, I am not satisfied with the chapters in the 3 subjects. I don't even have one chapter with full confidence. Beast, have you start off with the same order in which I have been conducting the classes? By the way, we have reached the end of the class. Yeah. Quickly smash the like button and subscribe in case you haven't done that. See, I'll tell you guys, the best order to complete the syllabus is exactly there in this playlist. Okay, in the order in which I have been conducting the classes date wise. Okay, so 11th standard chapters are there first. We are doing all the mechanics part, Newton's laws, work energy, everything is done. Okay, then electrostatics, ray optics, capacitors, circular motion, everything is there. I'll be arranging it again. So all the lectures, whatever are there, 11th standard, do it separately, 12th standard, do it separately together. Trust me, you'll be able to complete it, but higher weightage on 12th than 11th. But in 11th, most important thing is mechanics. So at least do till work power energy, basics. Then go to center of mass rotation, that's okay. Eventually center of mass rotation will be needed, but at least do till work power energy before going to 12th, or else you will not appreciate 12th standard electromagnetism. Once you do these things, you're doing fluids, thermal, waves, oscillations, modern, becomes very easy. They are scoring. You have time before Diwali, try to complete as much as possible. And when I say get confidence, you don't have to do advanced questions, it's okay. Do mains level question. Do level 1 of Tatva, level 2 of Tatva. Do basic questions. Let's say HC Verma, you're taking short answer questions, objective 1 questions. If you're taking DC Pandit, do objective 1 or level 1 questions. Do solved examples, do the class examples, do the DPPs, assignments which I have been giving you. Do this much. Trust me, you will see a lot of change in your attitude. You will see that, yes sir, I am able to do these questions, and JEE mains is not going to be difficult. It is going to be straightforward. Yeah, few questions, 15% to 20% will be difficult, but bearing that, even if you get 70 to 80 marks in every subject, you will be much above 99 percentile. Getting my point? So it's not about completing everything. It's not about 100% confidence. Even if you are doing 80% of the questions correctly, 80% of the syllabus is covered, 80% of confidence is there, you will be able to do it. You will be able to get much more than 99 percentile. Okay? So don't give up. Keep fighting. Keep attending. Keep practicing. Sleep less. Give away your luxuries. Focus. Be around positive people. Surround yourself with positivity, motivational quotes, charts, everything. You have to work every day, improve every day. Your today has to be better than yesterday. Tomorrow has to be better than today. Only then you are improving. Forget about mock test marks. It's okay, but give mock tests. When you complete a chapter, give a specific class test or a part test on that. That way you can see how well you are preparing. Okay? Cool. All the best, guys. I'll be seeing you in tomorrow's class of Center of Mass. Take care. Hasta la vista. Bye-bye. And do not forget to like, share and subscribe. Okay? Bye-bye. Take care.